record on this computer. All right. So let's get the PowerPoint up. And I need to share that screen. But I can never remember which one it is. We're going to share this one. Let's see how that works. Okay. All right. So we're going to talk about mass spectrometry, correct?
Yes.
We've been talking about the pieces and parts of mass spectrometry, and we just got to the fun part, which what is it useful for? You know, looking at the mass spec and figuring out empirical formulas. But I think we talked a little bit about this, didn't we?
We just talked like
Every time I do this, there's a little bit of a issue. It just needs something to kind of like that spark with hydrogen and oxygen. It's spontaneous as long as it gets started. Okay, so I think we mentioned that you can figure out, you can determine the molecular weight from some spectra. Electron impact, we said that about 80% have a molecular ion peak, and you can figure out the molecular weight from that. If you can't, the other 20% of the time, you might have to use some other technique, some softer technique like chemical ionization. And there are ways for us to determine whether it's a +1 or a -1 peak. Oh yeah, we looked at some of this, and I pointed out the handout that I'm going to give to everybody, and I gave you one. And it looks like this. In case you can see it on the little screen. That handout also has a couple of other things that are going to be very important for us. But before we get to that, let's look at, there's a couple of different ways you can get the empirical formula from a mass spectra. If you have a high resolution mass spectrometer, then you can use the molecular ion peak to determine the empirical formula from the exact mass, or a very accurate mass. So there's two methods. One is that, here's number one, but number two would be using the isotope peaks. We're going to spend most of our time looking at the isotope peaks, but if you actually had a table, if you have high resolution, those that we're going to the 10,000 place in the molecular mass. And so if you have a high resolution instrument, you're going to be able to measure the molecular mass pretty accurately. And notice that off to the left column, it says 83 and 84. 83 is a nominal mass. So 2 carbons, 2 times 12, that's what we mean by nominal. 1 hydrogen, so that's 1. 3 nitrogens, each one's 14. And we're saying oxygen is just 16. Now we know that they have different isotopes, but that's nominal.
It's all ballpark, right?
Yeah. Well, they're actually the lowest, usually the smallest smallest mass isotope region. You have carbon 12, which is 12. And so if you look at the far, notice that there's about 12 compounds or empirical formulas or molecular formulas that have exactly that nominal mass. So on a quadrupole or ion trap, you might not be able to distinguish between those different. They're all going to appear to have the same mass. But if you look at them more accurately, you notice that there's some differences. There's a slight differences in the molecular mass of each of these. And you're starting to see some effect, number of electrons, how many neutrons and protons, things like that, that are a little bit slightly different in mass. Remember, a proton is just a little bit lighter than a neutron. And an electron is about 1/1800th of the mass. Yeah, we usually ignore it, but here it's starting to show up. And so you can distinguish, if you have 83.0133, then you say, oh, that's C4H3O2. Okay. So that's one thing, one way to figure out the empirical formula or the molecular weight. Of course, the other is going to be using isotope peaks, so we're going to spend some time on that. Fragmentation patterns, what do they give us? How do they help us identify a compound? Well, they give us fragmentation patterns that give us functional group information. You'll be able to see certain losses. If you have a molecular ion peak and then you have a loss of 15, well, that's a loss of a methyl group. Loss of 29 would be an ethyl group. Loss of 37 is 37 would be a 39. 39.
Oh,
29 and 12. I guess maybe would be 37. Would be the loss of a. No, that's not right.
I would need a calculator. I can't do this stuff in my head.
I have to add a 14 to it. That'd be a 53 or something like that. But you can see certain losses, and you can look at those pieces that were lost, and kind of get a picture of what's left behind.
Mm-hmm.
Okay. And the other way is to compare your spectrum to reference spectra in the spectral lab. So that's a good way. But remember with our GC mass spec experiment that when you did that, you get a quality point. Like if it's 100, if the quality of match is 100, then it's a perfect match.
Mm-hmm.
But it's never a perfect match, and you have lots of compounds that have a pretty much the same match. So sometimes it's not.
That's why we have other tests they're on.
Yeah,
So
probably if we weren't using GC mass spec, if we're looking directly at just a mass spectrometry that way, it'd work a little better. All right. I had to mark on the screen to get it to react. Okay, just to remind you that if you do use a spectral library, that has to be done at 70 electron volts. The libraries are
because they're
built
all,
that way.
yeah.
And so that's what most instruments are set to. We could actually lower that 70 electron volts, maybe use 40 or 50, and it's going to be a slightly gentler fragmentation. And you might be able to pull a molecular ion peak out of that if you lower the energy of that. But these do give you lots of fragmentation. What are the factors that affect fragmentation? Well, weak bonds break more easily, right?
Mm-hmm. Also, I would say the bigger the molecule, the more fragmentation you have.
Yeah, that's probably true. You get a lot more ions. What else? Certain structures are more stable. Aromatic rings, anything that's kind of conjugated might be a little stronger. It doesn't always give the molecular ion peak, right? This is just a characteristic of any mass spectra, but there's always going to be a base peak. And a base peak is the peak that's the largest. And what they do is they take that base peak that's the largest, and they convert it to 100. So for instance, if that base peak was 195, 1.9 times 10 to the 6. What they'll do is they'll take that, multiply by 100 and divide by 1.9 10 to the 6, and you get 100. But then they do the same thing to every other peak in the mass spectrum. And what that gives you is that gives you relative ratios of those peaks. We're going to do that with isotope peaks in just a little bit. We're going to normalize it. Okay, isotope peaks. These are the, if we have a molecular ion peak, or if you have a fragment peak. Fragment peaks have isotope peaks as well. Because remember, an isotope peak is basically you're going to have a nominal peak, like if you have a methyl group, CH3, that'd be 15. So you'll have a peak at 15, but you'll also have a peak at 16, because you could have a carbon 13 in a compound, in a molecule. So it'd be one bigger. And you might have a hydrogen 2 along with a carbon 13. So you could have a CH3, you could have a 17 peak. You're not going to see a 17 peak though. And the reason for that is that hydrogen is 99.99% hydrogen 1 and only 0.01% deuterium. So the probability of it is really, really, really low. The probability of carbon 13 is somewhat low, at about 1%. It's 1.1%, I think. So, and those probabilities, what's the probability of having different isotopes in a set of compound? Well, those probabilities are going to determine the relative sizes of the isotope peaks. And here's a picture. Well, this is a table in your in that handout I gave you for mass spec, and you can see that up here, hydrogen. Let me just define some of these. These are the natural abundances. So 99.99% hydrogen 1, 0.01% hydrogen 2. Carbon is 98.91 and 1.1%. And then you can see you go down. Phosphorus there's only phosphorus 31, 100%. And iodine is 100% as well. And fluorine, 100%, yeah. So there's some elements that don't have naturally occurring isotopes, yeah. Now, notice these things right here. This X plus 1, this is sort of an M plus 1, an M plus 2. Okay. So what that does is it tells you how much contribution, if you set the largest peak in the set of isotope peaks to 100, what contribution would you have for a carbon, for any possible carbon 13? So if you have 100 for your main peak, if you have carbon,
usually 7.1.
Yeah, if you have CH4, then the M plus peak would be 100, and the M plus 1 peak would be just 1. Would be 1. So this would be 100, and this would be 1 for that peak. There's a little bit of contribution. If you have 2 carbons, there's a potential you could have 2 carbon 13s in it. But the probability of that is really low. And so these are the contributions that you would expect to see. So if you have oxygen, it's going to contribute to the M plus 2 peak a little more than it will to the M plus 1. Nitrogen will only add to the M plus 1. And here silicon adds quite a bit to both. Phosphorus, sulfur rather, adds 0.8, 4.4. Some of these halogens, notice iodine and fluorine don't add anything, but chlorine adds about 1/3. So if you have 1 chlorine in a compound, you're going to have, this is going to be 100, and this will be 33.
Dr. Campbell he told us that's how you can determine chlorines and
Mhm.
stuff, but I never knew why. So
We're going to look at that.
it's due to the isotopes. So.
Yeah. And bromine is, it says 98. So if you have one bromine, you're going to have one peak that's 100, and the next peak is basically going to be 98. Because look, there's a 50, almost 50-50
Yeah.
proportions between the two isotopes. We're actually going to go through and calculate what these isotope peaks and their relative sizes for a compound, and we'll see how that works. Kind of look at it backwards. Okay, so oh, by the way, carbons. This is another table over here on the right that's kind of useful. If you have one carbon, it's going to add 1.1 to the M plus 1 peak. If you have 9, you're going to add 9.9. And you can go pretty high. And at some point, you're going to, if you have enough, you might start seeing some contribution to the M plus 2 if you have enough carbons. It's all about probability. Okay, so a couple things that we can get from the isotope peak. We can figure out how many carbons in a structure in an unknown compound. We can figure out the number of halogens and their type, particularly chlorine and bromine. There's something called the nitrogen rule, and it can tell us something about the number of nitrogens that are in a structure. If you have a molecular weight, if the M plus peak is even, right, then you have either 0, and that's usually the case, or you could have 2, 4, 6, an even number of nitrogens. Because remember, nitrogen has a mass of 15.
14.
Oh, 14. But it only, I know I'm trying to think of it. It only forms 3 bonds. So an odd number of bonds. Everything else forms an even, well, except for singly.
Yeah.
But if you put if you put hydrogens around the carbon, you always get an even number. Fluorines, you get an even number. Oh, nitrogen, that's it. If you have nitrogen, then you have an odd number of, well, you have one loss lacking. But anyway, if you have an odd number, a molecular weight, then it's going to be an odd number of nitrogens. That's for the M plus peak.
So the M plus 1 peak?
M plus peak.
Oh, M plus peak.
The molecular ion. So it's the compound just lacking an electron. Yeah, when I mean the M plus 1, I'm going to put the 1 there.
Okay.
Yeah.
I just make sure.
Yeah, I understand. Let me tell you this though. This is only for if you look at a fragment of that molecular ion peak and look at its isotope peaks, its first peak is going to be an odd number. It's going to be odd because you've broken off something, right? It's missing a bond. So it's going to be odd. Like if you have CH3 and you break a bond between the carbon and one hydrogen, you have 12. You have 15 now rather than 16. That's always going to be the case. Okay. So that's an important rule, and we'll look at we're going to look at some handouts. Rings plus double bonds. You remember that?
A little bit.
I'm not sure where I'm going next. Here it is. Here's a little equation. Here's a number of carbons. Here's a number of single, like hydrogen, fluorine, chlorine, things that only attach in one place. These are like nitrogen. I'm trying to get it correct in my mind. It's been a while. Let me take a look at this real quickly. Yeah, yeah, Z is nitrogen, phosphorus, things like that, which can have 3 bonds, and then you have to add 1. And so if you have an aromatic ring, then what you would have is you'd have 6 carbons. You subtract, you have 6 hydrogens, right? 6 divided by 2. And then you would add, you have 0 over 2, right? Plus 1. So this is going to be a 7 minus 3 is 4. And what that tells you is you have 1, 2, 3. From this, you have 3 double bonds. Right. But also, notice this is 4, so you have 1 ring. When you form the ring, you lose 2, just like you lose 2 hydrogens if you made a double bond.
Yeah.
So that can really help you when you look at the actual empirical or molecular formula. You can kind of say, oh yeah, this has to be aromatic.
Or it just has this many double bonds.
Yeah, you have an oxygen in it, but it has 1, therefore it has to be maybe a carbon oxygen double bond.
Is that so? That tells if it's a carbon oxygen bond as well.
Well, it won't. It could be it could be an alkene with a hydrogen alcohol, I guess.
Okay.
But it tells you have at least 1 double bond in it. So, oh yeah, I should just got a little. That wasn't bad to look. Okay. Okay, let's look at a couple of spectra, just kind of, and we'll get to isotope peaks here in just a little bit.
Okay.
Now here's a mass spectra.
It looks fun.
And you see there's a lot of fragmentation, and it's possible this is a molecular ion peak right here. And usually molecular ion peak is going to be the one that's furthest, the biggest, right? Now, if there are some peaks right, so we're going to say this is M plus, and now there could be some peaks just 1, 2, and 3 greater. So this is the M plus 1 peak, and if you look closely, it's 116 mass to charge ratio. And then we can look at some of the fragments or some of the what's left after the loss of something. So if you look at that one right around 80 something, 87 mass charge ratio, that's the loss. That's a difference of 29. If you go from if you take that 116 and subtract 87, you get 29. And so this is the molecular ion minus 29. And it makes sense that is C2H5, the ethyl group. You can look at the next fragment. Now, what doesn't happen is one molecule doesn't lose an ethane, and then right after that lose another piece. All that energy goes into the molecule, and it probably to break a bond, it has to kind of be in kind of one place. And when it breaks, it's used up.
Okay.
So each of these fragmentations are different molecules, a different set of molecules.
Different fragmentations.
Yeah.
Yeah.
So here, some molecules do lose an ethane group. Others can lose something else. And if you look at this is 73, and that could be the loss of C3H7.
Lose the purple group.
Yeah, that's the loss of 43, which is the loss of a purple group.
The next one is going to be butyl group, is it?
Well, maybe. Let's take a look. What is it? This looks like it's around 50 some, 57.
No.
But you can add a 16 to this, or a 15, and you could lose this. This is not exact. This should be a loss of 60, I believe. But what you find is that hydrogen sometimes can be a little mobile. I mean, you break a bond and you have these electrons sitting there.
Yeah.
And in that process, in the activated complex for that, hydrogen might move from one fragment to another. And that's kind of why you get a lot of these, this grouping of fragments. There's a little movement of some molecule, of some atoms, particularly hydrogens, within a structure as it breaks up. And so this is loss of 15 actually. This is from here to here would be 15, so it's probably that. And you can see down here below, I'm kind of indicating that when you lose the ethyl group, you have a mass of 87. That's what this all weighs over here, right? This is all 87. And if you lose that propyl group, you should get this would give you an ion with a mass of 73. And if you break it here, and you're left with this over here, that would be just basically a butyl group, right? And a butyl group would be 48, 49, 50, 51, 52, 53, 54, 55, 56, 57. And that's kind of what you have here. Or maybe I did my math wrong there. So this is actually 57. That's one of the reasons why it's showing up, is that it's the after you lose this part of the molecule, you're left with a butyl, which is this peak right here, isn't it? It might maybe the better view of it. Maybe this right here is the loss of 58, which would be the loss of this, I guess. Or 59, I guess. Loss of that. Okay, and you have some more fragmentation. These are probably differ by about 14, approximately 14. This is about 29 or 8. One of these might be an ethyl group with a positive charge, and then this grouping over here is about 14 more. This is about, this is 29. I'm sorry. This would be This would be ethyl group. And so this could be a propyl group. And probably the strongest, this one right here, this peak right here is probably a CH3, CH2, CH3. And that seems to make sense, right? You're going to you can break it here or here. And so there's two sources of propyl groups. And that'd be 36, 37, 38, 39, 44, 42, 43. And that should be around 43 in here somewhere. Okay. It's really hard to, if you don't have the empirical form, if you don't have the molar mass, it's really hard to go through these fragmentation. It makes sense.
So, will the
and some of these peaks make no sense.
So it just give you the mass charge and you go backwards from there?
That's what I do. I'd start, if I have the molecular ion peak, and then just say, well, what about this peak?
Yeah. Okay.
What could it possibly be? I look at the different loss, and it will tell me maybe it's a methyl, maybe it's ethyl, propyl or something, or chlorine or something. And then if I can't figure out anything, well, I don't know. And you go to the next peak, and maybe that'll help you. Sometimes there's things that happen that are a little more complicated. These are, after all, really energized molecules that can do funky things. Here's another example. What do you think is in this molecule? Where's the molecular ion peak?
So would it be the very right?
Yeah, the far right.
And not the bromine?
Yeah, exactly. This is 110 and this is 108.
which makes sense.
Yeah. I mean, if they're equal in size and there's a difference of 2 between them,
Then you would have to subtract the bromine from the overall, which
Yeah.
I don't know what the charge is.
well, think of bromine. What's the,
35, I think,
that's chlorine. Bromine is
50 something,
70,
57.
79.
Oh,
79 and 81.
got those backwards then.
And if you look at this, this is basically 79 and 81. 80 is right in the middle. Right in the middle, and then they're on either side.
Oh, okay.
Yeah.
Why are the peaks so tall?
Well, that's must be fairly stable. That's what a tall peak is, a peak that's more stable. You produce more of them and they're stable.
Abundance.
So as they drift through from the ionization chamber into the mass analyzer, they don't fragmentate
Yeah.
for much. What about this? These are pretty close to being the same, aren't they? These are the same.
It can't be another bromine, can it?
It could be a fragment that has bromine on it. What's the difference in this size right here? That's the molecular ion peaks. This right here is a loss of 15. Going from here to here, there's a loss of 15. And so that'd be the loss of a methyl. And going from here to here, you have a loss of 29.
Ethyl group.
Ethyl. And that gives you bromine.
Yeah.
So we can figure out what this is pretty easily. Basically that, right? That gives you 79, that gives you, well, 93, and that gives you 79. And this fragment here, this is right around 29, isn't it? Yeah. Right around 29. Which will be some part of, well, it'll be mostly ethyl group. But there's one of the things that, if you have bromine or chlorine or fluorine, these are fairly electronegative. And when they fragment and leave a molecule, sometimes they take a hydrogen along with
Well, yeah, that makes sense because it's trying to stable itself.
it. Yeah. And so, you know, there's maybe a peak of 20 or 30 here. Or no, I'm sorry, up for 28 here, as well as 29. And there's hydrogens, I don't know, things go on. Yeah. Lots of bromine. I'm not sure why I put this here. This is about 29, actually. Like 27 to 29. Here's another one. This one I like to show. I'm not sure why rugged, compact, and fast scanning is there. Ignore that. But what do you think you might have here?
I don't know. It's
What is this? What does this up here tell you? I mean, all this.
you're gonna say chlorine in it, but it doesn't. I don't know. It's
Yeah, chlorine would be more like this,
Yeah.
1/3.
but that
Bromine would be basically the same. But remember, if this is chlorine or bromine, then this would be a difference of 2.
yeah.
And these 2 peaks right here are just 1 apart.
Some sort of I don't know. Some sort of isotope.
Well, could be just the loss of a hydrogen, couldn't it?
Yeah.
Like if you have an aldehyde or sometimes an alcohol, sometimes you can lose just the 1 hydrogen. But there's other places this could happen. And so when we look at this, if this was the if this was the M plus peak, let's say this one was, and this is 1 greater, it could not be.
Mm. Yeah.
Because there's no way, unless you have a bromine, there's no way this peak, well, this has to be M plus 2, but it's M plus 1. And there's nothing that's going to be, that's going to lose or contribute this much to the M plus 1. You go down through that table of abundances and you'll see that nothing will. I mean, you might have a few like down in here, but so this has to be the loss of just 1. This actually happens to be toluene. How does that happen?
We would have to probably lose it. I don't know. On that carbon, I don't know, Chief.
You don't know?
Actually, it would be on the it would be the on the methyl group, because if a hydrogen kicks off, it's already stable in it.
Yeah. If you lose 1 hydrogen,
And
what you end up with is, I think, do I have it on next slide? No, it's called propylamine. Down here I have it. Let's try to get over here. So
it just kicks the hydrogen all over.
let's try to go over here to
Or the plus part.
is it this one? I'm going to erase everything. So what happens is you lose one of these hydrogens, and this carbon goes down into the ring.
Mm-hmm.
And it forms this very stable. This is an aromatic.
Yeah, it just pushes the positive charge around.
Mm-hmm. Oh, propylamine. Anything, benzene will give this peak. Oh, I'm sorry, benzene won't. Anything that has a CH2, maybe even a CH, I'm not sure about CH, though, just CH2, and it cuts it off. You can cut it off here and you get this propylamine. Very stable, so it's usually going to be one of the largest peaks.
Makes it a great acid.
Maybe so. I guess you've talked about propylamine somewhere else.
Maybe. Makes it a good acid, let's say that.
Yeah. And over here, these are just ring fragments. And you can kind of look at, and there might be a loss of about 12 or 13 for each of these. This is around 60, maybe 60. This is 64, maybe. And this is like 50, around 52 or so. And this is what, 38 maybe. So these groupings are about CH apart, you know. And so you're starting to see pieces of the ring. That's about it. Now you can look down here and you can see that this is the molecular ion peak right here. And you have some isotope peaks. And if that's 80, and this is about 5, so this is about, if you convert this to 100, this would be about 25% bigger. This would end up being about 6.25 or something like that. And so this tells me that I have, 5 or maybe 6 carbons. Actually, I have 7, but I can't. I'm doing bad math here because that's hard to measure. But you can figure out the number of carbons from that.
Mm-hmm.
Right here. Okay, real quickly, if you wanted to look at these, actually figure out what isotope peaks would appear and the relative heights, we can go through and do that calculation. Based on the natural abundances, hydrogen 1 is going to be 99.99, right? 99.9. Carbon is going to be 98.9. Chlorine 35. This is carbon 13 or carbon 12. This is going to be what, 75.77, right? So how do we calculate probability? What's the probability that you have carbon 12 and only carbon 35? This would be the smallest mass of 84. So that'd be 12 plus 2 plus 70 would be 84. Right? And so if you have this, and it's just a probability calculation.
Mhm.
You know, the probability of carbon 12 is 0.989. The probability of, we ignore the hydrogens,
Mhm.
they're just 0.999. And the probability of carbon 35 is 0.7577. But we have two of them, there's two possibilities, so it doubles it. And so this would be the overall probability of having this peak. And that means this is going to be the largest peak.
Mhm.
So what I can do is I can take that and multiply it by 100 over 0.563, and that gives me 100. And then you go to the next one, one mass bigger, and there you'd have a carbon 13 would get that. That's the only way to get a carbon 13 if you're not considering hydrogen. And so carbon 13 has a 0.011 probability, and these will be the same for chlorine, this. And so the peak will be relative to 100 would be 1.12, and that's 1.1, so one carbon.
Because that's the only percentage for the carbon 13.
Yeah. And for one more mass, there, the only way to get that would be to have one of the chlorines be a chlorine 37. And so the probability of having one chlorine 37 is the probability of a carbon 12 times the probability of a chlorine 35 times the probability of a chlorine 37. But there's two possibilities of this, right? Because either chlorine could be chlorine, the chlorine
So they
70.
so the carbon can't do that, right?
37.
So
No.
because the
Because there's only one place for it. There's only one carbon.
yeah, okay.
Yeah.
I see what's happening.
See, this could be 37, carbon 37. This could be carbon 35. Chlorine, I'm sorry. They both start with C. This chlorine could be 35 or 37. This one could be 37 or 35.
So now I'll look back at the CH2Cl2. There's two chlorines.
Yeah.
So.
Yeah. And so that gives us this, and it gives you this relative size. And then you go to 87, and there you'd have a one chlorine 37 and carbon 13, but there'd be two possibilities because of two chlorines. It'll give you a relative size, which is not very large. And then 88, you got both could be chlorine 37, but there's only one possibility for that.
Yeah.
And so you have 10.32. And then for 89, you'd have everything elevated, like chlorine 13 and both chlorine 37.
So this mass charge ratio, the higher the number, the further right it would be on the graph on the x-axis.
Yeah, these numbers. Yeah.
All right. So and the peaks over here, what we got, the higher the number, the bigger the peak is.
Yeah. So this is 100. This is 84.
Mm-hmm.
85 would be about that.
Yeah.
And then 86 would be 64, which would be up in here somewhere. And then 87 would be just a dot. This should be bigger. And 88 would be about 10. Would be about, and 89 is
as simple as could be.
And when you look at this chart, there's also another table right here that shows you the what relative sizes you would expect to see for one chlorine, two chlorines, three chlorines. You see, for two chlorines, it'd be
the 35.
kind of what we did over here. It gives the actual numbers. Be 165 and 10.6. Close to what we. we're not considering the hydrogens. The hydrogens have a little effect.
Mhm.
So that can tell you how many chlorines you have.
Yeah.
Well, we're going to, well, there's another slide here. If you just have CH3 and 1 chlorine. There's, it's about a third. This is about a third of this. And we're going to actually, oh, I didn't realize I was in there. I'm sorry. I went through all that. I didn't think I had the slide in the PowerPoint, so I copied from one place to another.
No, but what you did, it made perfect
Yeah.
sense.
Here, this is what we're going to get to next on Monday. We're going to look at how to determine the empirical formula from those STPs. That's the last thing
Okay.
in this chapter.
We do.
I think so. All right, let's turn you off. Hopefully, hope to see you Monday. Lara, I always want to pronounce it Lara.
You have a good day.
You too.